Hello everyone, my name is Yuuki Takano, and let us introduce our research that is a STAP, Scalable and Flexible Traffic Analysis Platform running on commodity hardware. This is a research for technology of application-level traffic analysis. This is a table of contents. First of all, we introduce a motivation. Why did we develop STAP? And then we show related work and our research. And third, we show the design of STAP. And fourth, we show the implementation of STAP. And fifth, we show the performance evaluation. And finally, we give a conclusion. Okay, this is the first motivation. Well, it is the first motivation that is we want programmable application with traffic analyzers. That means we want to write traffic analyzers in any languages, such as Python, or Ruby, or C++, for many purposes. For example, someone wants to implement IDS or IPS in Python, or someone else wants to use C++ for machine learning. So, and we want not to write codes handling TCP stream reconstruction, because that is quite complex to handle TCP stream. And we want modularity for many application protocols. And we want to separate application analyzing logic and TCP reconstruction logic. Here is a second motivation. That is, we want high-speed application level traffic analyzer. That means we want to handle high bandwidth traffic and high connections per second flows, TCP flows. And to handle such a high bandwidth traffic, it is required that that the architecture is horizontal and CPU cross scalable. It is a third motivation. That is, we want it running on commodity hardware is a third motivation. That means we want open source software and we not to use expensive appliances. The appliance is good, but sometimes quite expensive for use. Then we show related work and our work. Here we classify related works into three classes. Our first class is a class for low-level traffic capture. For example, DPDK, NetMap, which are currently developing class fit into this class, and PCAP, BPF, maybe you know, is class fit into also this class. And second class is a class for flow-oriented analyzer, GASP, SCAP, and LISA15 is class fit into this class. And third class is a class of application traffic detector. That is just detect which protocol is in application level. Well, L7 filter, MDPI, and review proto ident are classified in this class. And our study STARP is classified into two classes, which are flow-oriented analyzer and application traffic detector classes. And furthermore, STARP has features of modularity and scalability. Well, this picture shows the high-level architecture of STARP. Well, STARP mainly consists of two parts. The first part is STARP cell incubator. It captures high bandwidth traffic from the network and separates and forwards to multiple STARP cells. On inner STARP cell, flow abstractor and analyzers are running in the cell. For this architecture, we achieved horizontal scalable and core scalability. Then we show the design principle. Flow abstraction is a first principle of STARP. Well, STARP abstracts flows by application level protocols, and it provides flow abstraction interface we called like /dev, /proc, or BPF for many programming languages. Modular architecture is a second principle. The modularity completely separate analyzing and capturing logic. So it can easily replace analyzing logic without stopping capturing logic. Horizontal scalable is a third principle. Generally, analyzing logic tends to require many computer resources, so therefore it requires the horizontal scalable. So volume effect should solve the problem. And finally, for CPU core scalable is fourth principle. Both analyzing and capturing logic should be core scalable to analyze high bandwidth traffic efficiently. Then we show the design of STARP. Well, we defined 4 planes for STARP. Well, capturer, separator, abstractor, and analyzer planes. Capturer planes capture traffic from network by using ordinary technologies such as layer 2 switches, port mirroring, and separator planes separate flows and forward to the cells. The flow abstractor abstract flows and provide flow abstraction interfaces to analyzer plane. In analyzer plane, there are many analyzers. For example, forensic or IDS IPS analyzers located in these places. And we assume that user implements these analyzers. Then we show the design of stop cell incubator. Well, first, packet forwarder captures layer 2 frames from the network, and if layer 2 bridge mode is enabled, the packet forwarder forwards to another interface, network interface, to enable layer 2 bridge. And the IP fragment handler receives packets from the packet forwarder, and it handles fragmented packets. And finally, the flow separator separates flows to multiple interfaces by using IP addresses and port numbers in packets. Then we show the design of stop flow abstractor. Well, the IP packet defragmenter first receives packets from network interface, and it defragments IP packets if needed. And then flow abstractor receives packets from the defragmenter, and identify flows by IP addresses and port numbers of packets. And then TCP and UDP handler reconstruct TCP flows. But for UDP packets, it does nothing. Then flow classifier classifies flows by using regular expressions. These regular expressions are provided by a config file. Finally, classified flows are outputted into flow abstraction interfaces. And on the right-hand side of this picture shows the interfaces of flow abstraction. For example, HTTP flows are outputted into HTTP interfaces, and TLS flows are outputted into TLS interface. Analyzers connect to these interfaces and receive flows and analyze these flows. Then we show implementation. Well, this stop cell incubator is implemented in C++11, and it uses netmap and available on FreeBSD. Oh, okay. And the stop flow abstractor is also implemented in C++11. It uses pcap for netmap. In our paper, it uses only pcap, but we updated the flow abstractor to use the netmap last week, and it is available on Linux, BSD, and Mac OS X. Source code is available on GitHub, and it is distributed under 3 classes BSD license. Then we show the performance evaluation. This picture is this picture shows packet drop against connections per second of the flow abstractor. In our experiments, Snowd drops packets when 4 kilo connections per second and node drops packets when 10 kilo connections per second. But however, our implementation, the step flow abstractor drops packets when 50 kilo connections per second. Then we show the variation of the cell incubator. Well, right hand side picture is picture shows the network interfaces of the cell incubator we use for experiment. Well, it has 12 1 gigabit Ethernet network interface and 2 10 gigabits network interfaces. And we measured alpha to gamma only and alpha to beta only, and both alpha to beta and alpha to gamma. Well, in our experiments, the step cell incubator can handle up to about 12 mega packets per second. That is quite a good performance because of we adapted NetMap. Other features, well, L7 loopback interface is provided for encapsulated flows, and load balancing mechanism for application mechanisms is provided, and separating and mirroring modes of step cell incubator also provided. But we can not show details in this session. So see more details in our paper, please. Then we give a conclusion. We propose STAP for application level traffic analysis. STAP has following features: flow abstraction, running on commodity hardware, modularity, and scalability. We show STAP has achieved high performance in our experiments. Okay, that's all. Thank you for your listening.
Any questions for our speaker? No, microphone.
What platforms did you implement SF-TAP on where you tested the scalability? In other words, did you have a cloud farm, Docker, Apache Web Service? How did you, can you talk more about how you scaled it, how you added more nodes or removed nodes when you didn't need them, and so on like that?
Currently, we experiment on the physical machine, and we ensured the SF-TAP work on Docker, but we have not measured performance of that. Maybe it is our future work.
Okay, let's thank our speaker again.